The final talk for the session will be on HybridSA, GPU acceleration of multi-pattern regex matching using bit parallelism, and the talk will be given by Alexis.
Thank you for the introduction. So I would like to present to you our latest work, which is a GPU-CPU heterogeneous engine for multi-pattern matching. So first, let's talk about the regular expression. So in general, when we talk about regular expression, there are three kinds of operators that we have in mind, which are the concatenation, union of clay and star. But we also encounter in real-world regular expression other operators that are regular, like bounded repetition, look around, or not, like back references. The general approach when we want to do matching of a regular expression into first transform it into an equivalent automaton, and more particularly into a non-deterministic finite automaton. In our work, we use the Glushkov construct to do this because it has a neat property that is useful for bit parallelism that is called homogeneity. So here is an example of an homogeneous automaton. What you can see is that for every state, if you look at the incoming edges, they're labeled by character class. They all have the same character class at their incoming edges. For instance, state Q2 has character class BC as incoming edges for both the self loop and the loop and the edge coming from state Q0. Therefore, what we can do is instead of labeling the edges, we label the states. And this is going to be useful later on. And we also represent the final states like here with this representation. So the key computational problem that we want to solve in this work is the multi-pattern matching problem. So what we have is a set of regular expressions, and we want to find the occurrences of those regular expressions over an input text. So first, let's talk a bit about the GPU programming model to understand how we can do NFA simulation on the GPU. So it is often referred to as single instruction, multiple threads, because we have many threads that must execute at each step the same instruction. There are several problems that can occur when you create a program on the GPU. The first one is called divergence, because sometimes you may have two threads that are going to execute different instructions. Another thing is when you have threads that must communicate, you have to synchronize their shared variables to have a consistent value. Another thing to keep in mind is data locality, because you would like threads to have coalesced memory access to use the cache instead of the global memory that is much slower to access. So on the GPU, the typical way to do NFA simulation is as follows. You have a set of threads, like here I showed thread 0 up to 3, and each state is assigned each thread is assigned a different state. For instance, here state Q0 is assigned to thread 0, state Q1 is assigned to thread 1. And what is going to happen is we have here the pseudocode for NFA simulation that is going to be executed by each of those threads. And what happens is we're going to iterate over the inputs. And at each step, what we're going to do is first activate the initial states. We're going to have a synchronization to have a consistent value for the next bit vector. And then every thread is going to check if its state is active or not, and then going to iterate over its successors. And if the successor label matches the current character, then we're going to set the bit as the position of the successor. And then we update the active state. So there are several issues if we want to port that algorithm to the GPU. The first one is you have a lot of synchronization at step 3 and 8 that can slow down the performance. Another thing is if you look at those highlighted in purple between line 4 and 6, you have a lot of branching because some of the threads might take the branching and some might not. For instance, at line 5 here, we're iterating over the successor of a given state. So if you look at thread 0, it is responsible for the state Q0 that has two successors that are Q1 and Q2, whereas thread 1, responsible for state Q1, has no successor here. So thread 0 is going to have more work to perform than thread 1, which can result in imbalance. So those are the two main issues. As I said, the most existing GPU regex engines, they use a variant of this algorithm that I just showed you. And this can give rise to divergence and requires synchronization. So the main issue of divergence is that it can lead to the serialization of the instruction execution and therefore can reduce the throughput. The thing is, GPUs are actually good when you have the same instruction to be executed by different threads over multiple data. This is why in our work, we focused on bit parallel algorithms such as the classical shift-n because we think it's a good fit to support certain classes of regular expression that have simple transition patterns on the GPU. So first, let's introduce the shift-n algorithm on this regular expression here. So we represent the NFA that is created by the Glaunec construct here, and below we have the active states. And the first idea of the shift-n algorithm is that the active states are going to be encoded in a register. And here the register is going to be of size 4. And if state QI is active, then we're going to set the ith bit starting from the right as at 1. Like for instance here, state Q0 is activated after reading letter A in the input ACD, so we put a 1 below it. The other idea of the shift-n algorithm is that we're going to be able to simulate the NFA only using bit parallel instructions that are bitwise OR, bitwise AND, and shift left. So let's go through a series of instructions to simulate the NFA here when we consume letter C. So first, we're going to simulate the transition by performing a shift left by 1, activating state Q1 and deactivating state Q0 here. Then, because the initial states are always active, we're going to activate the initial state using a bitwise OR here. Then, we only keep the active states that are matching the current character, here, letter C. This is why we are deactivating state Q0. And finally, to compute the output and check if there is a match, what we do is we compute the intersection between the set of active states and the set of final states. Here, because Q1 is the only active state, but it's not a final state, we don't report a match. And this operation is performed with a bitwise AND. So this algorithm has several advantages if you compare it to the algorithm I presented before, the standard NFA simulation. The first one is one thread, instead of simulating only one NFA state, is going to simulate one NFA at a time. And this solves many problems that we had before. The first one is you don't need communication between the threads because NFAs are independent, therefore no synchronization. Another problem that is solved is about divergence. Before you had this for loop to iterate over the successors to take all the transitions. No, because we're only using one instruction, a shift left, to perform the transitions, we don't have divergence anymore. There are still some limitation of this algorithm. For instance, it can only simulate transition of the form state QI to state QI plus 1 that look like a line. Moreover, there is also a restriction on the number of NFA states that must be at most the size of the register. And this is indeed a restriction. There are many regexes in the real world that look like this one here, AB02C. And here I colored in different colors the transition with different distances. So in red, there are the transition of distance 1 that we could support with shift-n. But the transition of distance 2 and 3, we cannot support them with shift-n. So the question that we want to solve is, can we extend this shift-n on the GPU to accelerate most regexes on the GPU? And the answer of this paper is yes. We propose extensions of shift-n and rewritings that enable us to accelerate about 80% of the regexes on our data sets over the GPU. And the main idea that we have is to use an heterogeneous approach using the CPU and the GPU to accelerate the vast majority of regexes on the GPU and run concurrently the rest on the CPU. So this is how our architecture looks like. We have a set of regexes here in blue. And what we're going to do is, during a compilation step, we're going to split them between the GPU and the CPU. On the GPU, we have several specialized kernels, about 80 of them, that are running concurrently, such as the classical shift-n or shift-n disk, which is an extension of shift-n to larger distances. On the CPU, we're running multiple instances of Hyperscan, which is a state-of-the-art CPU engine, one per CPU core. And so during this compilation step, we must choose whether the regex is going to go on the GPU or on the CPU, and for the GPU, which kernel we're going to use. So we're going to see now how we perform this compilation of the regex set. So we have many extensions of shift-n that we call kernels that are used to support regexes on the GPU. For a given regex, what we're going to do is we're going to choose the cheapest kernel that can execute this regex. How do we know which one is the cheapest? It's because one property of shift-n is that it's input independent because it doesn't depend on the active states. So we know exactly what the performance is going to be like. And on the right here, you can see a plot of the throughput in function of both the distance of the transition, the maximum distance, and the register size. As expected, the throughput decreases when you increase the register size or the maximum transition distance. And we also have rewriting rules that are going to help us later on to move a regex to a cheaper kernel that we'll present later. Another question is, how do we choose if a regex should be executed on the GPU or on the CPU? To perform this operation, we have a greedy algorithm that is going to start by the cheapest kernel only. And every time we're going to check what is the performance of the global algorithm. And we're going to keep adding more and more kernels until the load between the CPU and the GPU is balanced because they're run in parallel. Once we found that point, we're going to record the set of kernels and use it to split the regexes. And by that, I mean all the regexes that are supported by this set of kernels go to the GPU, and the rest goes to the CPU. Now let's talk a bit more about the rewrite rules that we use. The first one is called the distributivity rewrite rule. The main idea is to distribute the union of our concatenation to reduce the maximum transition distance. Here we have this NFA, and as you can see, the transition with the longest distance is the one in red here that is of distance 4, and we would like to reduce this. So what we're going to do is we're going to duplicate those orange states here and create 2 lines instead of this complex structure. And by doing that, we're able to reduce the maximum transition distance from 4 to 2. And so the benefit of this approach is, first, it can help us to move a regex from an expensive kernel to a cheaper one, or even a regex that was previously executed on the CPU could be executed on the GPU. It is, however, a trade-off because we lower the maximum distance, but by doing that, we had to duplicate the states in orange here. A second rewrite rule that we use is called the bounded repetition rewrite rules. There are many regexes that use this operator, bounded repetition, and we use this identity here that you can see to reduce the transition distance again. So what we do is we're going to split this transition of distance 3 into 2 transition of distance 2 here in blue. And again, this allows us to reduce the maximum transition distance from 3 to 2, and it can actually be generalized to all bounded repetitions. Now, I would like to present the experimental result that we have for HybridSA. So we have considered many application benchmarks ranging from virus signatures to bioinformatics with protein motifs. And first, what we observe is that using our strategy, most of the regexes for the split are executed on the GPU, about 80% of them for most of the data sets. Then if we look at the choice of kernels that are executed on HybridSA, we notice that for this ProSite and Yara dataset that have generally simpler regexes, the classical shift-hand is enough to execute most of the regexes on the GPU. But this is not the case for more complex datasets, such as Snort, Spam Assassin, and Suricata. And for those, we can see that there is more diversity in the kernels that are executed on the GPU because there are more regular expressions that are larger, so you need a bigger register size, 64 bits or 128, and there are also longer transitions there. We have performed a comparison against a state-of-the-art engine on the CPU that is called Hyperscan and a state-of-the-art engine on the GPU, which is called OOPSLA, as well as a combination of the two because we're using both the CPU and the GPU. So to have a fair comparison, we created a hybrid engine and 2 versions of it. One that uses the same split of the regexes as HybridSA, and another one that uses a training step to improve the throughput. What we observe on this plot here, that plus the throughput normalized to hot start, what we observe is that HybridSA is actually consistently faster than all the other state-of-the-art engine that we've compared it to. Compared to one of the state-of-the-art GPU engine that is hot start, we have a speedup that is about 30 times to 200 times. And we also observe that the rewriting rules, so this is HybridSA opt here on the plot, are actually useful for the more complex datasets, such as Suricata, Spam Assassin, and Levenstein, bringing higher throughput. So to summarize, what we've shown here with this work is that the bit parallel algorithms are actually a good fit for GPU execution. And instead of a full CPU or GPU engine, a heterogeneous CPU-GPU engine enables us to accelerate most of the regexes on the GPU, while the ones that cannot be efficiently executed on the GPU can be executed on the CPU. We also see that the rewrite rules help improve the performance, and our implementation has good performance against the state-of-the-art engine on the CPU and the GPU. Thank you.
Questions?
Hi, thank you for your talk. It was great. So I have a question that did you consider any CPU optimization in your implementation, like any SIMD instruction or any parallelization in the CPU side based on your implementation of GPU?
In this work on the CPU, we kept it to just parallelizing hyperscan. We didn't do more optimization on that side. We focused more on the GPU end.
And also, I have another question, if it's possible to ask. So, how do you handle the data transfer problem usually that is happening in GPUs? I mean, did you consider it in the choosing between CPU and GPU? For example, for large regexes, you prefer to put it in the CPU instead of transferring it to the GPU. Did you consider this or no? It wasn't a challenge.
So if I understood the question well, is did we consider for larger regexes whether we should execute them on the GPU or on the CPU?
Yep.
Yes, so we did that. So maybe I can go back a bit. Where is it? So actually here. So we have several kernels where we increase the register size. So basically the register size is analogous to the size of the regex, because if you have less than 128 states, for instance, we need a register size of 128 or something like this. So yeah, here we limit ourselves to 256 because we noticed that after this, the throughput is so low that it's not worth it to use it on the GPU. So those regular expressions that are too large are going to be executed on the CPU because it's easier for.
Thank you.
Sure.
Question?
Hello. Awesome talk.
Thanks.
Can you comment anything about the how much the thread divergence has reduced in terms of before the optimization and after the optimization? Any comment about that?
So the question is about how the optimizations are used, or
how did the thread divergence change? How much has it reduced, or
okay. So actually, no, there is no divergence at all compared to the previous work that had this NFA simulation algorithm that I showed, a variant of it. So for us, because we use those bit parallel operation, we don't have divergence at all. This is the main advantage of it.
Oh, I see. Thank you.
Sure. And same for synchronization. It was also part of the question.
Yeah, I had one last question.
Okay.
Did you do any experiments to see how robust your speedups are across different CPU models or GPU models?
We focused on an Intel CPU. We didn't do it, but it would be interesting to see that. For the GPU, though, we tried on different instances, and what we observe is that because we have a lot of parallelism, so here those results are actually on GPUs that you can run. It's not like a server's GPU. So if you had a server GPU, the throughput would be much higher because the parallelism that we have is, right now we're limited by the hardware in terms of the number of total threads that you can execute simultaneously. So it would be even larger, and the speed up again, the CPU would be larger as well.
Very cool. Okay, let's thank the speaker again.